Hello, Year 8. Here's the answer to your starter here. So, this vertex, we go a vector of 2, 0 to get to the mirror line. So our vector on the other side is negative 2, 0. Then this vector is 0, 0. So when we reflect it, it stays 0, 0. So we have a vertex here and one there. We join them like so. And this is a kite. This here, our vector to get to our mirror line is 0, negative 4. So our vector on the other side of the mirror line is 0, 4. Same with these ones. If they're on the mirror line, they get reflected there. My lines are getting worse, I'm sorry. Okay, this vertex here, we go negative 2, 0. So our vector on the other side is 2, 0. This vertex, we go negative 4, 0. So our vector on the other side is 4, 0. Join those up. Here we have a trapezium. If you want to be specific about it, it's called an isosceles trapezium because these two sides are the same length. This shape here, because all of the sides are the same length, this is, I don't know why I wrote a P there, this is a rhombus. And finally, this shape here, so here's our vertex, we go 0, negative 3. So our vector on the other side is 0, 3. Join those up like that, and this is called an arrowhead. This shape isn't going to give us a quadrilateral when we, well, it will give us a different quadrilateral when we reflect it. Here, our vector to get to the mirror line is negative 1.5, 1.5. So our vector on the other side is going to be 1.5, negative 1.5. So that's going to take me to here. My vector to get to the mirror line here is negative 2.5, 2.5. So my vector on the other side is going to be negative 2.5, 2.5. This vector is negative 3, 3. So on the other side, it's going to be 3, negative 3. And this vector here, if we have a look, goes all the way through there. So that gives me negative 5, 5. So on the other side, it's going to be 5, negative 5. And these shapes are both trapeziums. They're right-angled trapeziums. Okay then, today's lesson we're going to be looking at rotation. We're going to learn how to rotate a shape about a centre of rotation using vectors. We're going to start with identifying rotational symmetry of shapes though. So all two-dimensional shapes have some rotational symmetry. The degree of rotational symmetry that an object has is known as its order. So these are the orders for all of these shapes. Now for any shapes that have order 2 or higher, they have a single centre of rotation, which in these cases are those red dots. If a shape that only has an order 1 rotational symmetry, anywhere on the shape can be a centre of rotation. So the order of rotational symmetry that an object has is the number of times it fits onto itself during a full rotation of 360 degrees. So you see when I span that shape around, it only fits on top of itself once. In this shape, I'm just going to pop a spot there so I know where the beginning is. I can rotate it like this, it fits exactly on top of itself there, and then again when we've gone all of the way around. So that's why it's order 2. Similarly, for this shape, there's 1, 2, 3 times it fits on top of itself, so it has order 3. 1, 2, 3, and 4. So that shape has order 4 rotational symmetry. Okay, from page 61 in your supplementary book, I would like you to find the order of rotational symmetry of all of these shapes and think about which capital letters have rotational symmetry. Pause the video while you do those questions and mark them. Okay, so a rotation occurs when an object is turned around a fixed point. When we're describing a rotation, or we're told to do a rotation, we need to know 3 things. Firstly, the angle of the rotation. Now, these are the only angles you're going to need to know: 180 degrees, 90 degrees, and 270. So they're quarter, half, and 3/4 turns. The direction of rotation. So you might need to go clockwise, which is the way the hands turn on a clock, or anti-clockwise. Now, you won't need to worry about this now, but if you're not given a direction, you assume it's anti-clockwise. The third thing you need to know is where your center of rotation is. That's the fixed point about which the object moves. So let's have a look at an example. Here, I'm told to rotate the blue dot 90 degrees anti-clockwise about the green center. So this is my center of rotation. That doesn't move. Here's my blue dot. I'm going to work out the vector to get to my blue dot. So it's 1 across and 3 up. So my vector to get to my blue dot is 1, 3. I'm going to rotate my vector rather than the dot here. So 90 degrees anti-clockwise. This 1 is going to go from here to here if I rotate it 90 degrees. And the 3 is going to go from being vertical to being horizontal. So my blue dot, when I rotate it, my vector now, you'll see, is -3, 1. And that's where my blue dot ends up. If I wanted to produce the same dot with a different rotation, I could go clockwise instead. But instead of going 90 degrees, which would take me to here, I would go 270 degrees clockwise. If I wanted to end up where I started, I could rotate by 0 degrees or 360, or any multiple of 360. Okay, more often than points, we're asked to rotate shapes. So let's have a look at the triangle to begin with. Same as when we were reflecting and translating shapes, we're going to actually just think about rotating the vertices and then we're going to join them at the end. So this vector to this vertex here is -4, 0. If I rotate that 90 degrees anti-clockwise, it rotates down to here. So that's my new rotated point for this vertex. I'm going to change the colour so you can tell the difference between them. This vertex here has the vector 0, 2. When I rotate that 90 degrees anti-clockwise, ends up here. So that's where my green point ends up. And so my triangle rotated 90 degrees anti-clockwise ends up there. You might be able to picture that in your head without using the vectors, but the vectors will come in useful in more difficult questions. For my rectangle here, here's my center of rotation. This vertex is the vector 0, 1. So when I rotate that 90 degrees clockwise, this vertex will end up here. This vertex here is -3, 1. When I rotate -3, 1, 90 degrees clockwise, that becomes 3, 1. So that vertex will end up there. This vertex here is -3, -1. So when I rotate this shape 90 degrees clockwise, that gives me 3, -1. So that vertex is there. And then this vertex is just 0, -1. So when I rotate that 90 degrees clockwise, it ends up here. And I join my vertices together. That's my rectangle. Here, where my centre of rotation is not on my shape, this is when the vectors come in especially useful because they're more difficult to picture. So let's start with this vertex here. My vector is 1, 1. This time I'm rotating by 180 degrees. So this vector is going to rotate all the way round to this. So 1, 1 becomes -1, -1. I'm going to rub this out so it doesn't get too messy. Let's do this vertex next. That's 2, 4. So when I rotate that 180 degrees, that gives me -2, -4. That's my second vertex. And finally, this one over here, I get -3, 2. So when I rotate this round 180 degrees, I get 3, -2. That's where my vertex is. I join my 3 vertices together. That gives me my rotated triangle. And you notice that 180 doesn't say clockwise or anti-clockwise. That's because either way I rotate, I would end up at the same place. Have a go now at the sheet that I sent you if you were able to print it. Each time rotate the vertices individually and then join them up at the end. If you don't have a printer, then you can use this link, which I also sent to you, to rotate these shapes instead. The origin is 0, 0. Note that all of the centres of rotation are about the origin. Now, if you wanted to have a play around with rotation, you could go to this website here. Looks like this when you first get there. And if you scroll down, you have this interactivity that you can play with. So you can choose which shape you want by clicking here. You can change what the shape looks like by moving the dots around, and then you can rotate them. We can show the vectors. So you see here, if I rotate this by dragging this other green spot, I can see how my shape and my vector move. And there's some suggestions just above, things you might like to be interested. What happens when you put the center of rotation on a vertex? Remember, vertices are corners. What happens when you put it on an edge? What happens when you put it inside? You can have a play around with what happens with rotations there. If you wanted to try some more challenging questions, then you can scroll down and there's some more challenging questions down here as well. That should be enough for you to be getting on with for now. So I will let you get on with your questions. Thank you very much.